and then I'm okay.
Yes, I'm starting now.
Okay, thank you. I'm starting. Hello everyone. I'm Şeyma Gülşen. I am at the TED University now, and my department is math. I'm in second class. Now, everybody, welcome to 10th Bar Mathematics meetings. Muhammed Vafik Hocam is going to make a speech that titles Primitive Prime Divisors of Sequences of Integers. Hocam, at the end of the meeting, I'm going to convey you to the questions that comes from YouTube or chat box. If you want to answer it, you can answer while the speech. That's your turn. You can start. Good luck.
Thank you. Hello, everyone. In this presentation, we will talk about primitive prime divisor of sequences of integers. So first, we can start by the definition. What is a primitive divisor? So if we have a sequence, Bn, which consists of elements B1, B2, B3, which are integers, we say that the term Bn contains the primitive prime divisor if there is a prime P such that P divides Bn, but P does not divide any Bi for I less than n. That means that P divides this element and does not divide any element before that. So a quick example, an easy example for that, I take the sequence k squared plus 1, where k is from 1 to 10. So if we take the first element, that is just 2. So 2 divides this element and does not divide anything before, so it's 2. Element number 2, that's 5. 5 does not divide anything before, so that is a primitive divisor. For element 3, that is 2 times 5. Both of them appear before, so there is no primitive divisor, and so on. So we can discuss some results that were found in old sequences, on some sequences. First, we can discuss Locus and linear sequences. First, we start by the definition. So what is the definition? For the Locus sequence, we take alpha and beta to be algebraic numbers such that alpha plus beta is in Z, alpha beta is in Z, and the GCD between these two numbers is 1. They are co-prime. And the last condition, alpha over beta is not a root of unity. So if all of these conditions are satisfied, we can define the Locus sequence by the elements un, where un is defined as follows: alpha power n minus beta power n over alpha minus beta. Quick example for that, if we take alpha and beta 2 and 1, the sum is 3 and the product is 2, these are co-prime, and the 2 over 1 alpha over beta is not a root of unity. So that means we can define the Locus sequence, which is defined as below. And this we can see it is exactly equal to the Mersenne numbers. So this is another way to study the Mersenne numbers is to study the Locus sequences. The other sequence is the lemma sequence. If alpha and beta are algebraic numbers with the same conditions, except that we take alpha plus beta squared to be in Z. It doesn't. It's not necessary to have alpha plus beta, but the square of that should be in Z. So if these conditions are satisfied, we define the lemma sequence to be if dependent on n. So if n is odd, we take alpha power n minus beta power n over alpha minus beta. And if n is even, we divide by alpha squared minus beta squared. Quick example, we can take alpha and beta as follows. The sum now is not in Z, but the square is equal to 5. So that's in Z. And we can check all of the other conditions, so we can define the lemma sequence as follows. And a quick note that if we take beta to be 1 minus square root 5 over 2, not square root 5 minus 1, so negative this beta, in that case, the sum will be in Z, which will be 1. And with that, we can define the Locus sequence. And that Locus sequence can be actually checked to be the Fibonacci sequence. Now, for these two sequences, we will just be mentioning some results that were studied before, because these are two of the very interesting sequences, so they have been studied thoroughly. So just we can mention some results, like if alpha and beta are integers, then for all n greater than 6, there is at least one primitive prime divisor for both the locus and lemma numbers. In particular, if n for all n greater than 2, there is at least one primitive divisor, except for the case alpha is equal to 2, beta is equal to 1, and n is 6. This can be its factorization. U6 can be U2 squared U3, so there's no primitive divisor for U6. If alpha and beta are in R, real numbers, but satisfying the other conditions, then the locus number can be defined, and in that case, we have for all n greater than 12, not 6. For the lemma number, we require alpha squared and beta squared to be in R, and again, there will be a primitive prime divisor for all n greater than 12. For in general, if alpha and beta are algebraic numbers in C in the complex domain, then both the locus and lemma numbers will have primitive prime divisor for all n greater than 30,030. These are just introduction to some results for the primitive divisors. Now we will go to study another sequence. First, I define what is a dynamical system. So a dynamical system is a set S together with a function phi. That's a self-map from S to S. This self-map allows iterations, where phi n, we can define phi n to be phi composed with itself n times. Now, with this, we can define also the orbit, forward orbit of a point. So if we take a point, that's an element in S, and we keep applying phi to this alpha. So we will get the forward orbit. That is the set phi n alpha for n greater than or equal to 0. All of the iterates of alpha. And for n equal to 0, this is phi 0 alpha. This is just alpha itself. This is the identity map. One more definition before an example. If we take alpha to be an element in S, such that alpha is a critical point for phi. Critical point, as in calculus, the derivative is equal to 0, or it has a pole at that point. Then the orbit of alpha is called the critical orbit. So now we can take a quick example for that, for all of this. So if we take S to be the real numbers, and phi of x is x squared plus 1. And this function will have a critical point when x is equal to 0 by just the derivative. So we can see the critical orbit of this function to be phi 0 of 0, which is 0, and then phi of 0 is 1, phi of 1 squared plus 1, this is 2, phi of 2 is 2 squared plus 1, that's 5, and so on. So this is just a quick example. Now we will try to examine a specific case, a specific family of self-maps of dynamical system. That is, phi x is equal to x power d plus c, where d is greater than 1 and c is an integer. And for this case, we will derive a proof for the following theorem. That theorem is due to Kevin Dirksen and Anna Heinz. The theorem says, let phi of x is equal to x power d plus c, where c and d are integers and d greater than or equal to 2, assuming that the critical orbit is infinite. So if c is plus or minus 1, then the critical orbit will have at least one primitive prime divisor for each element in the sequence, except for element 0 and element 1. So for all n greater than or equal to 2, there's at least one primitive prime divisor. For c does not equal plus or minus 1, then all of the elements will have a primitive prime divisor from n greater than or equal to 1. We will try to prove this. Now we will just introduce a few lemmas before proving this one. So first, we start by a lemma. If we have the function as specified before, and choosing a and z such that the absolute value of a is greater than or equal to c, and the absolute value of a is strictly greater than 2, then the sequence, which is the orbit of a, is strictly increasing sequence. The proof for n is equal to 1, we can see that phi of a is greater than phi of 0 as follows. A power d plus c, this is the triangular inequality. And because a is greater than 2, the absolute value of a is greater than 2, so a power d minus 1, we can take it to be 2. And since a is greater than or equal to c, so this is greater than or equal to a. to a minus a, and this is equal to the absolute value of a, which is phi 0 of a. So it is increasing at n is equal to 1. With here, there's a strict inequality. And by induction, we can do the same, but for phi n plus 1 and phi n. And again, we will see its strict inequality here. So using this, we can check which orbits can, which C's will induce infinite critical orbit and which C's can induce a finite critical orbit. So first we can check for C greater than 0. So C greater than 0, x power d will always be greater than C because C is an integer in that case. So C, x power d will be greater than or equal to C. After the first iteration, I mean, and then plus C, that's again increasing. X power d is greater than x, sorry, not greater than C. So in that case, it's an increasing sequence. And so it will have an infinite critical. For C less than -2, we can check the first iteration, phi of 0, this is C. So the absolute value of C, because C is less than -2, then the absolute value of C is strictly greater than 2. So now for n greater than 1, we can write the critical orbit to be the orbit of phi 0. And by last lemma, we can know it's increasing, strictly increasing. So again, since the sequence is strictly increasing, then it doesn't repeat, so it's an infinite critical orbit. Now the finite critical orbits, so now we are looking for C and Z. So the missing cases are C equals 0, -1, and -2. For C equals 0, it can be seen that the critical orbit is just the element 0. It will be periodic point, just 0, 0, 0, and so on. If C is -1, and if D is odd, then the sequence will be strictly decreasing. This can be checked. You can check the second iteration. It will be satisfying phi 2 will be -2, and phi 3 will be sorry, no, it will be less than or equal -2. So you can apply the same lemma, and then it will be strictly decreasing and infinite. For D is even, phi of 0 is -1, phi of -1 is 0. So the critical orbit is just the two elements, 0 and -1. So that's a finite orbit. For C -2, we can check that if D is equal to 2, then the critical orbit is 0, -2, and 2. And for D is greater than 2, also again, it can be checked easily that phi 2 of 0 will have an absolute value greater than 2. And hence, again, we can use the same lemma. Now, another definition. We define a rigid divisibility sequence. So if we take an integer sequence, Bn, and for any P, this sequence has two properties. If the valuation of Bn with respect to P is greater than 0, then the valuation of Bnk is equal to the valuation of Bn. So any multiple index will have the same valuation. And if two elements have valuation greater than 0, then they have the same valuation, and it is equal also to the valuation of the element with index being the GCD of the two indices. So with that, first we have a lemma that our critical orbit for these functions is a rigid divisibility sequence. So the proof, first, let's take 1' to check its properties. So assuming that the valuation of phi n of P is equal to E, which is greater than 0, for some n greater than or equal to 1. This means that if we write it in mod P power E plus 1, it will not be 0, but it will be a multiple of P power E. So if we check phi n plus 1, this P will be multiplied by D, which is greater than 1. D is greater than or equal to 2. So that is greater than P power E plus 1. So this term will turn to 0, and the other term, and there will be plus C, so that will remain, but that is equal to phi 1 of 0. So this is phi n plus 1 is congruent to phi 1. By induction, we can see that phi n plus t is congruent to phi t, mod P E plus 1, and also we can, another induction, we can have phi k n plus t is congruent to phi t. Now we should prove the two properties. The first properties we can start with, if we have that the valuation of phi n is equal to E, then phi kn, which is equal to phi of k minus 1 times n plus n. By what we just proved here, it is congruent to phi n, modulo p power e plus 1. So that valuation is equal to E, because this is congruent to p power e times something. So the valuation is E, which is equal to the valuation of phi n. Now, if we have the second property, if we have two elements with valuation greater than 0, and without loss of generality, we assume that phi m has a valuation greater than phi n. So, and by Bezold identity, we can write the GCD between m and n to be mt plus nk for t and k integers, and we will work modulo p power e2 plus 1. So phi of the GCD can be written as phi of mt plus nk, but since we are working modulo p power e2 plus 1, so what we proved can work on m. So we can remove the mt, so that is congruent to phi nk. And by the first part, this is congruent to phi n of 0. And because p power e1 is less than p power e2, so less than p power e2 plus 1, this is just congruent to p power e1 times some constant. So that means that the valuation of the phi of the GCD is equal to e1. And by the first part, phi n and phi m are both multiples of phi of the GCD, so their valuation will be the same and equal to E1. So now we proved that this sequence is the divisibility sequence. Now we will write another way to factorize phi n. First, we can write it as a product of primes, and we can collect the primes that are primitive divisors for phi n as p's, and the non-primitive part, q's. Or we can write it as pn times nn, where pn is the product of the primitive part and nn is the product of the non-primitive primes. So we will have a lemma that will be using the divisibility sequence. That lemma is the non-primitive part of n, of phi n, is equal to the product of the primitive parts of phi d, where d divides n and d less than n. So we can prove that, we will see. So let q be a prime such that the valuation of q in nn is equal to f, which is greater than 0. So any prime dividing nn. And let's look at it. So if it is if it divides nn, then it divides phi n of 0. And since it's non-primitive, then there is some index d where q was primitive to d. So q was dividing by d. However, by last lemma also, q will divide the GCD, the phi of the GCD of d and n. But since q is primitive to d, that means that d is the least index, but q also divides the GCD, the phi of the GCD. So that means that GCD of d and n is greater than or equal to d. And of course, this means it's equal. So d divides n. So PD is a primitive part for an element with an index dividing n. So, and also by last lemma, because d divides n, so valuation of phi n is equal to the valuation of phi d, which will induce valuation in nn, because this prime is in the nn part, will be equal to the valuation of PD, because this is in the primitive part for phi d. And q appears in the primitive part once, so if we multiply by the other primitive parts, the valuation wouldn't change. So that is equal to the valuation of the product. So that is for any prime divisor of nn. So that means that nn divides this product. The other side is, can be seen trivially, because if d divides n, then by last lemma, the primitive part divides nn. And since these pk's are pairwise coprime, so we can multiply them and dividing nn. So that proves this lemma. Now we come to the theorem. So having that phi x is equal to x power d plus c, we will check this first. In here we separate the first two iterations. For the first iteration, that is phi 1 of 0 is equal to c. So this will not have a primitive divisor only if this is 0 or plus or minus 1. So if c is 0, the critical orbit is finite, and we take that the critical orbit is infinite. For c plus or minus 1, this is treated independently. We don't check n is equal to 1 for c is equal to plus or minus 1. The second iteration, c power d plus c. This is c times c power d minus 1 plus 1. So the first option is phi 2 of 0 is equal to 0 for it to not have a primitive divisor. That means that c is 0 or c is equal to minus 1 and d is even. So that this can be equal to 0. And in both cases, the critical orbit is finite. Or the other option, it has a primitive divisor. It has the primitive part, the primitive part, which is c power d minus 1 plus 1. This is plus or minus 1. So in that case, again, the analysis will show that either c is minus 2 and d is 2, or c is 0. And both cases, again, have finite critical orbit. So this is for the first two iterations. The rest, we first try to prove an identity for m greater than or equal to 2. This will be used. So first, for m is equal to 2, looking at this identity, this is the absolute value of phi 2 of 0, strictly greater than just phi 1. And this we saw by the lemma and multiple parts that these orbits are always strictly increasing. So this is trivial for m is equal to 2. Now by induction, we assume it's true for all m less than or equal to m minus 1, capital M minus 1. So we can rewrite, this is true for m minus 1. That means this strict inequality, which translate because we are working with integers. So this can translate to less than or equal phi m minus 1 of 0, the absolute value, minus 1. We can use that. Phi m, we can write it as phi m minus 1 power d, greater than or equal triangular inequality. And then because d is greater than or equal to 2, we can change this to 2. And c is exactly phi 1. And because of the strictly increasing sequence of phi's, then we can change phi 1 with a strict greater than minus phi m minus 1. And we can take phi m minus 1 outside, and this we just saw here, it is greater than or equal the product. So just this proves that it is true for capital M. Collecting all information, we can just write this inequalities. So NN is equal to the product of these divisors, which is less than the product of all the divisors less than n, which is less than or equal the product of all of the phi's, because these are just parts of the phi d. And we just proved here, this is strictly less than phi n of 0. So in other words, the primitive part, which is phi n of 0 over nn, is strictly greater than 1. Since it's strictly greater than 1, then there's at least one primitive, then one prime divisor dividing Pn, at least one prime divisor. So that means, and Pn is the primitive part, so at least one primitive divisor for phi n of 0. Now I will just be mentioning some further results. This were a simple result that could be introduced now. For further results, we can check these. First, what we derived now is for C is in Z. If C is equal to A over B, it's a rational number, then we can define again the integer sequence to be the sequence of numerators of phi n. So there was a result by Holy-Krieger that says for any choice of C in Q, there will be at least one primitive prime divisor for an, except for finitely many n's. And more than that, the maximum number of these n's is 23. That means in the orbit, there's a maximum of 23 elements with no primitive divisor. The others must have primitive divisor. And there are even lower bounds for specific conditions on C, depending on the range of C. So we can see a question emerges when we say phi of x is x power d plus c, and taking A to not be in the critical orbit. How many elements in the orbit of A has no primitive prime divisor? This can be another question. Another result, maybe not directly into the count, but into the density. So another result shows that for the density of the primes that appear in the orbit of a function of this form, x squared plus c, and zx is 0. The density of the primes, this means then counting the primes that appear in the orbit and dividing by the total number of primes and taking the limit as x goes to infinity. So this density is 0. So the question can come, does all orbits of all functions have prime density of 0? Another question can be, what if we change the sequence? If instead of taking phi n of A, we can take phi n of A minus A. We actually have some examples with prime densities greater than 0. So what kind of sequences can have positive densities? Thank you for listening.
We are thank you, Hocam. Let's check the questions. At the chat part, we have no question actually. On YouTube, again, we have no question, unfortunately.
I have a question.
Yes.
Okay, we are listening.
So can you go back to slides to Locus numbers?
Locus numbers?
Yeah, I think you stated some odd number, like 30,000 something, like for the primitive prime divisors you stated about. Yeah. Do you know how they get to this number?
I have the reference. Actually, I can send it to you. Okay, maybe just a second. Actually, it is primes generated by recurrence. No, existence of primitive prime divisor. Okay, maybe I can. Should I share it with you?
No, I see it. Okay, I'll find it. Thank you.
Okay, welcome.
Are there any questions? Okay, Hocam. I'm finishing. So again, thank you for coming and informing us. At another meetings, we want to see you again.
Thank you. İnşallah.
Thank you. Arkadaşlar ben şimdi bir de demek istiyorum. Bundan sonra Mehmet Haluk Şengün hocamızın eliptik eğrilerin modülerliği başlıklı konuşmasıyla saat 14.20'de devam edecek.